All right, I turned the recording on, so we're officially um started today. So the end of our second week. We get a break on Monday, so that's nice because that's Labor Day, so we will not be here. All right, so I'll see you again a week from today. So hopefully we can get through some things today, so you'll be able to work on this space coordinates homework uh, over the weekend. And so this homework vectors in the plane. I don't know why I'm pointing at the screen. So this homework vectors in the plane. This is due tonight, right? Um, so here's your last chance to ask questions about that if you have questions about that, right? Okay, Fatine has a question. Hang on, Fatine, and I'll get to that in just a second after I finish my other spiel, but maybe that was the end of the spiel. Um, and so that's all I've got posted so far on the homeworks. So we'll be adding to that next week, right? Um, as soon as we get past our introduction to space coordinates, as opposed to just regular old uh, two-dimensional coordinates. Um, so I am determined today to pass out the roll, so do not let me forget that. Although everyone is accounted for, so I don't have to turn names to the registrar as put anybody on the naughty list for not attending class in the first couple of weeks. So that's good. We're going to do some more graphing today. So if you need some graph paper, let me know. I'm also going to give you, as promised here, this chart here. And then once I give it to you, then never use it. Anyway, there's a front and a back. A couple of ways of remembering trig values, special angles, like 30 degrees and 65 degrees. I'm going to just tell you my shortcut memorize accent, accent. That one is just committed to memory. But it is useful always have to be able to recall these uh, from memory right without having to um, rely on a calculator. And so here's my system. Um, let me explain it to you. Have to remember, you have to remember, let me stay near the camera so people can hear me on the tape. So, I messed up the, so Fatine was telling me I messed up the tape from Monday. I didn't mess it up, but I didn't publish it properly. So, so when he pointed that out, I published it. So the link is working now. If you tried looking at the tape from Monday, the YouTube tape from Monday, I think it's now corrected. All right. So look, if you have to remember that sine of zero is zero, right? So you have to remember that sine of zero is zero. But you want to take that. So look in that sine column, which is that middle column there on this front page, which has got the table. The second page has a graph on it. But so but you want to, so you have to remember that sine of zero is zero. But you want to think of that zero in kind of an unusual way. You want to think of zero as being the square root of 0/2. Right? Because all of these sine values for special angles are going to be square root of a number divided by 2, right? Now, sometimes they can be simplified, like square root of 0 divided by 2 simplifies to 0, right? Okay, but you want to think of them in that fashion in order to help you remember. So it's always square root of a number divided by 2. And then as you're just going up in the first quadrant through the special angles, you just always add one under that radical. So sine of the next special angle is going to be square root of 1 divided by 2, right? Sine of the next special angle is going to be square root of 2 divided by 2. Sine of the next special angle is going to be square root of 3 divided by 2. And then finally, sine of the next special angle is going to be square root of 4 divided by 2, right? Okay, so it's very easy just to remember that pattern. Square root of 0, 1, 2, 3, 4 divided by 2. Now, you're moving up through the first quadrant for the special angles, right? So the first special angle is 0. Square root of 0 divided by 2 is 0, right? Second special angle is 30 degrees, or pi over 6. So that's for sine, that's square root of 1 divided by 2. But square root of 1 is 1, so you get 1/2, right? For the next special angle, which is 45 degrees, pi over 4, it's square root of 2 divided by 2, right? So you're always just counting up. For the next special angle, it was 60 degrees, which is pi over 3. It's square root of 3 divided by 2. And then the next special angle in the first quadrant, oh, really not in the first quadrant, but almost in the first quadrant, right, is 90 degrees, which is in the sign there is square root of 4 divided by 2. Of course, square root of 4 is 2. 2 divided by 2 is 1. So square root of pi over 2 or 90 degrees is 1. You see that pattern, right? Okay, so it's very easy to remember that pattern. And then for cosine, you just count backwards. So cosine of 0 starts at square root of 4 divided by 2. And then you go down. Next special angle is square root of 3 divided by 2. Next special angle is square root of 2 divided by 2. Next special angle is square root of 1 divided by 2, all the way up to 90 degrees for cosine is square root of 0 divided by 2, which is 0. Cosine of 90 degrees, remember, is 0. Okay, so that's my little system for remembering the sines and cosines of the special angle. And then to get the tangents right, you just divide sine by cosine, right? You just use that identity. Just divide sine by cosine, and you can get the tangent for the special angles, okay? Right, so I'm not good. We don't have to worry so much about secant and cosecant and cotangent, right? Although they're in that somewhere in that table. Memorizing those is not as important as memorizing sine and cosine and for the special angles. And then, of course, if you're in a quadrant outside of the first quadrant, you have to, of course, rely on the reference angle, right? So you have to find the reference angle for the angle, and then find the sine and cosine for the reference angle, and then adjust the sign properly, right, depending on which quadrant you're in. Well, this is not a trig class, so I'm not going to go through, doing all practicing all of that again, right? We'll recall it as needed for various problems if we run into trig values for special angles, correct? So anyway, you can have the chart. If you're used to doing special angles using the unit circle, there's the chart for the unit circle on the back. And it's also easy to memorize the sine and cosine for the special angles using the unit circle, right? But I'm not going to go through that system of using the unit circle to find sine and cosine, because I don't do it that way. But you may have learned it that way. So if you learned it that way, there's the unit circle on the back there, so you can remind yourself of how to find sine and cosine for the special angles from the unit circle diagram there on the back. Okay, all right. So much for that. Let's see now. So questions, right? So Fatine, you had a question. Other people have questions there from vectors in the plane, since that's due at midnight tonight, right? So be sure you try to finish that. If you run over, though, that's fine. Once you are past midnight, which is the due time, right, then you can request an automatic extension of the due date. And the instructions for doing that are somewhere down here, yeah, in the announcements on WebAssign, right? Okay, but make sure you wait till after midnight, after it's due, because if you request the extension before midnight, then I get an email and I have to physically do the extension. But if you wait till after midnight, I think you get it just happens automatically if you request the extension, right? You have to request it, but it'll happen automatically. But do that quickly. I think you have a window of like a day to request an extension, right? So to request an automatic extension, and then the points you get after the extension, you get a penalty, not for the points you had already earned, but for the new points you get after the extension. But it's still worth doing the extension and working for. It just adds points. It won't subtract points from your score. All right, Fatine, finally. Okay, let me open this and we can answer your question. I hope, maybe not. I'm in trouble. We're in trouble. Yeah, go ahead. 13. Is that the last one? Almost the last one. All right, so we had an example like this one, but then probably you couldn't find it on the tape, right? Okay, so let me remind you of the steps, and then but I won't go through all the steps, because now you can look at the example on the video, right? But we'll let's switch back to the notes here and we'll write that in. That may not be your version of the problem, Fatine, but we can fill in your version. Do you have your version written down, or is that the same? Oh, it's the same. Okay, good. Then we'll be working directly on your problem. So if you've got that written down, I'm going to switch back to the notes, so I won't be able to see these values, right? So you're going to have to fill them in for me. All right. So if I can find the notes. All right. So there are the notes that we were almost finished with for two-dimensional. Did I close it? There are the notes that we were almost finished with. Yes, I closed it. Let me find it again. There are the notes that we were almost finished with for two-dimensional vectors. We're going to switch to three-dimensional vectors today. We've got to finish that last example about the airplane, which is going to be kind of similar to this homework problem. All right, so tell me what information they gave us there. They told us that what the magnitude of some vector u is, was it the magnitude? Is 1? 1. Okay. And then they told us the direction of the vector is what? 45? Oh, okay. I thought it wasn't 90? Oh, okay. And then they told us about u added to some other mystery vector v, okay? And we know something about its magnitude, the sum, right? This resultant of the addition of these two vectors is what? What, root 2? And then the magnitude there, I'm sorry, the direction was 90. Okay. If we drew a picture of this, we could probably figure out actually without going through the formal steps here on paper what the vector v is. Isn't that what we're looking for? Information about the vector v. What do we want to know about v actually? Just the vector itself? We want to know its okay.
It's actually
Component form and then magnitude and direction. Oh, just find the component form of v. Oh, okay. All right. So okay. So remember, Fatine, the way we did this is ultimately we want to think of finding v as sort of simplifying this expression. So we're going to go about it kind of indirectly, right? Because u plus v minus u, notice that's going to be v, right? Because the u's will cancel. And we know something about u plus v, and we also know something about u, right? Okay. So and so I think we have enough information there actually to write out the vector u, and then we have enough information to write out the vector u plus v, right, in either component form or in standard form, right? Okay. And once we've got them in standard form, then we can fill them into this equation and compute what the vector v is, right? So, but you need to remember then how you can write a vector in component form using its direction, right? So the vector u in component form, you know that's going to be the magnitude of u, right, times the cosine of the direction, right, times I, times the unit vector I, plus the magnitude of u, right, times the sine of the direction, times the unit vector j. So this important formula, which applies to any vector, right, not just u, that's important for us to remember. Okay, that formula. So, but we can fill in the blanks here, right, and get the standard form for the vector u, right, because we know what the magnitude is, and we know what the direction is, right? So this is really pretty easy to do, right? The magnitude is 1. So they made that calculation simple for us. And then we have the cosine of 45 degrees, which is also easy to compute, right? And then sine of 45 degrees, which also is easy to compute, right? And you know now from your nifty table, right, that sine and cosine of 45 degrees is what? Square root of 2 over 2? that table that I just gave you, right? Okay. See, you know that because 45 degrees is the third special angle, right? So you start with 0. Sine of that is square root of 0 over 2. Next special angle is 30 degrees. Sine of that is square root of 1 over 2. 45 is the next special angle. We're moving up through the first quadrant. Sine of that then will be square root of 2 over 2. It's the same for cosine. So see how easy it is now to remember those sines and cosines for those special angles. So there it is, right? There's the vector u, just that easy. That's called standard form, but that's virtually the same as component form, right? Because in component form, this would look like this, right? Now, so we have to play the same game with u plus v, right? So we know that u plus v. One of the bad things about this laptop is I'm always touching this menu bar on the bottom. So u plus v is equal to its magnitude, right? Which is square root of 2, right? Times the cosine of its direction, which is 90 degrees times I, right? Plus its magnitude again, which is square root of 2 times the sine of 90 degrees times j, right? So this has got to be easy, right? What's the cosine of 90 degrees? What did we just mention that was? 0? Yeah, okay. So that's 0. So it looks like you do not have any horizontal direction at all, right? Any horizontal component to this vector. So this vector is going straight up, which of course you knew anyway because the direction was 90 degrees, right? And plus then the square root of 2, and the sine of 90 degrees is 1, right? So so you just get square root of 2 times j. And now you just fill in the blanks here, right? So you have square root of 2 times j, that's u plus v, right? Minus, and then be sure you put u in parentheses though, because it's got two terms. If we write it in standard form, square root of 2 over 2 times I plus square root of 2 over 2 times j. And so when we do this arithmetic, what do we end up with there? Well, you've only got one I term, right? So you have minus the square root of 2 over 2 times I, and then you have square root of 2 times j minus, when you distribute this minus sign, square root of 2 over 2 times j. I think that is square root of 2 over 2 again. Okay. So I think this is I think there's the answer. Okay, I'm not going to try to. I said I was just going to set it up for you, but there's the answer. I'm not going to try to type that in though. Okay, on the using the palette because it is a little bit of tricky to create this, right? You'll have to use the radical, right, to get square root of 2. I don't think you want a decimal estimate here. And then, of course, you have to use the palette to create the I and J, right? Instead of just typing those in from the keyboard as we did discuss last time, right? So does that seem to make sense there? Okay. All right. So I hope that's right.
And they asked to
Oh,
expect it to use.
oh, yes. Oh, so it asks for component form.
Yeah.
Yeah. So it is going to expect pointing brackets, right? These are really identical, but technically this is component form and this is standard form. Okay. All right. Okay. Let's see how much else I did any other damage to my windows here. I don't think so. All right. Let's finish our example from last time then, and that kind of is helpful with 14 because 14 is just a resultant. You're just going to create 3 force vectors given this information and then add them together to create the resultant vector, right? And then you'll have to use your resultant vector, right, to find the direction and the magnitude of that resultant vector. So I think we're doing that in that last example, but kind of indirectly though, because it's in this one is stated just sort of abstractly, but in our notes, the last example is actually embedded in a story about a plane, right? So remember, we had a plane that was flying a particular direction, okay, and so there's kind of a picture of that plane. Remember, it was traveling at a speed of 500 miles per hour. Its bearing was 330 degrees, so we had to kind of think about what what a bearing of 330 degrees means. That just means that if you measure an angle clockwise from north, that would be the direction of the angle. I mean, that would be the direction of the airplane. So if you go clockwise from north, in trig terms, that's an angle of minus 330 degrees, right? So there's the angle drawn. Okay, and but the airplane's traveling through some wind, right? And the wind is moving at a speed of 70 miles per hour at this angle. Okay, and so there's kind of a little picture of the wind force. And what we wanted to know was, well, once the plane, right, is blown off course slightly by the wind, right, then how is the plane actually traveling? At what speed and at what direction is the plane actually going to be moving? Okay, if it was sort of aimed in this direction but hits this wind of 70 miles per hour, right? That's blowing it and moving it in this picture a little bit more toward north, right? Okay, so we had set up the problem. The problem is really easy to set up. Okay, it's the arithmetic in this problem that's a little bit challenging, but the kind of the conceptual understanding of the problem is not that bad. So here's a vector that represents the plane, right? Okay, and so this is a force vector we're creating, or a velocity vector we're creating, right, to correspond to the plane. So the velocity is going to be the magnitude. I'm sorry, yeah, the velocity is going to be the magnitude of the airplane vector. So you'll insert 500 here, and then, of course, we know the direction of the airplane too. But we have to make sure that we translate that properly into a trig, correct? Not in sort of nautical measurements, but in more standard trig ways of measuring angles, right? So remember, the plane is traveling here at this bearing of 330 degrees, right? That means an angle measured clockwise from due north. So this angle is in trig terms minus 330 degrees, right? Because you don't measure angles clockwise in trig, right? But what that means is then that if you take the angle of the airplane from the x-axis measured counterclockwise, which is the normal way we would do this in trig, right? You would get an angle of 120 degrees. Is that right? Am I doing that correctly? Right, I think so. Okay. Because if this angle is minus 330 degrees, then this angle from the y-axis to the path of the plane, correct, is positive 30 degrees. This angle is positive 30 degrees, which means then that this angle from the x-axis is 90 degrees plus 30 degrees, or 120, correct? Okay, so so we use that, right, as that's the direction of the plane as we're going to be discussing direction, right, as we're going to be measuring direction. So that gives you this velocity vector that corresponds to the plane. Now for the wind, you can also represent that as a vector, right? The speed of the wind is 70 miles per hour. And what's the direction if we write the wind as a vector? Well, we're told, right, that this wind is moving 45 degrees, right? And so the direction from the x-axis for the wind would be 45 degrees. So you just fill in that as the direction of the velocity vector for the wind. And now, if you add those two, right, the resultant vector will give you actually now the velocity for that plane, okay, as it is traveling through that wind. So we just want to add those two together, and that resultant vector will be, we'll describe there then the direction and velocity of the plane once it encounters that wind. Now, of course, it's easy to add these conceptually, right? It's easy to add these vectors together. You're just going to add the two standard I components here, right? And the two standard J components here. But we need to do a little bit of arithmetic to actually compute now what's 500 times the cosine of 120 degrees, what's 70 times the cosine of 45 degrees, and so on and so forth, right? So we can actually add these two vectors together. Let's see if we can do that down here. So y'all may have to help me with the calculations. So I know what cosine of 120 degrees is. That's a special angle, but I'm going to have to multiply it by 500. So we might as well convert this to a decimal approximation. All right. Let's use a couple of decimal places there. So what's 500 times the cosine of 120? I have to calculate that. Can y'all calculate that for me? And we're gonna have to do this for all four of these terms, right? So if you want to, you can also work ahead there. So 500 times the cosine of 120 degrees. Y'all gonna make me do this? So there's 120, and there's the cosine of that. Well, minus 1/2, right? Oh, so easy. Okay, so I could have anticipated that, right? I said that was a special angle, so that would be easy. And then we just multiply by the 500, right? So it looks like it's going to be minus 250. So this is minus 250 times I plus, well, what is that? Now that's not going to be as nice, okay? So what does that turn out to be? 433. Did you get any decimal places, David? But you didn't keep them? Oh, okay. They're probably not necessary in the long run, but let's see what they are. So what we have 120, and I want to take the sine of that, right? So that's square root of 3 over 2. That is 0.866, by the way. And then times the 500 again. So that looks like it is going to be 433. Oh, it's very, very close to 433. Okay. So 443.01 times J. All right. What about the wind vector then?
Five.
49.5. You didn't keep the other decimal place? So it's 45. And then cosine of that, which of course is square root of 2 over 2. This is square root of 2 over 2 times 70. So 49 point, oh, I see why you got the half there. So yeah, so if we round that off, that is 49.50 times I plus then, and then sine of 45 degrees is the same, right? So this is going to be 49.50 again times J. And now just add those two together, right? To get the resultant vector. And so what does that give me? 200.5 I? Negative, yeah. 0.5 I. And then what's this one? 482.5. Oh, 51. Yeah, 482.51 times J. Okay. So that vector, that resultant vector, that sum vector, that is supposed to be the new airplane vector, right? If we take into account the wind speed. Now, what in the world does that mean, right? Okay, so what's the practical meaning of that vector? Okay, I mean, when you're just told that, that's sort of like, okay, so what? So you need to sort of analyze that vector, right? And by analyze it, I mean you want to find what its magnitude is, because that's going to tell you the velocity of the airplane. And then if you want to know how the airplane is traveling, which you probably do, right? You also need to find the direction of this this vector. Okay. All right. So let's find the magnitude, right? So you just have to do some more arithmetic here. So the magnitude of V is going to be the square root of, right? And now you have to square the two coefficients, right? So the minus 200.5 squared, right? Plus the 482.51 squared, right? And then, so add those two squares, right? And take the square root. Somebody want to tell me what they got approximately to a couple of decimal places there? Oh, this is supposed to be a 0.51. Sure, that's going to make much difference, but 522.50. Ah, okay. Somebody else get something similar to that? Do I have any confirmation on that? Got the same thing? Oh yeah. Okay. So if two people got it, then that must be right. Okay. So there it is. So see, that tells us, right, that the new speed of the, is that right? It's faster? Okay. So see, it's already violated my intuition. So this is a great thing about vectors, because somehow I would have thought that as being slower, but I guess it is somehow abetting it here just a little bit, right? Okay. Not much. So it really doesn't affect the speed of the airplane that much. But you might be interested in that, right, as a pilot, but that's probably going to change your fuel consumption, right? Okay, so there's the new speed. All right. And now what is the direction? Now look, now unless I'm completely crazy, right? Which is possible. I think for sure, right? The direction of that airplane's got to be shifted a little bit to the north, correct? Right? Okay. So I think we have to have a picture that looks something. Have to have a picture that looks something like this. So that means that that new direction, right, for that airplane is got to be less than, what was the direction before? 120, right? So I think it's got to be something less than 120. Okay, so if this doesn't come out less than 120, then my intuition is totally bad. Now, this is the hard part though, right? Okay, so how do we figure out there what is the direction of V? All right, so this is what's going to come up in that last problem too on your homework, right? Remember, you have to think of this in writing V in the correct form, right? Which is the magnitude of V, right? Times the cosine of its direction times I plus the magnitude of V times the sine of its direction times J. But we know what the magnitude of V is, right? That is what, 522.5? So times cosine of theta times I plus 522.5 times the sine of theta times J. And but we know more than this, because we know that this computation has to turn out to be what? Minus 200.5, right? So that has to turn out to be minus 200.5. And this calculation has to turn out to be 482.51. Well, just one of these two things we noticed here is enough for us, right? Let's take the first one. So I know that 522.50 times cosine of theta has to be equal to minus 200.5. So just divide both sides by the 522.5, right? So you have cosine of theta is equal to minus 200.5 over 522.50. And now apply inverse cosine to both sides. Okay. So so there you'll get that theta is equal to the inverse cosine of this number, right? See, when you apply the inverse cosine to both sides, when you apply it to the left-hand side, that should simplify to theta. Remember, there are sometimes some complications with that simplification, right? So you have to think carefully about where theta actually is in the rectangular coordinate system, right? So we may have to adjust this slightly, but theta is something like the cosine inverse of 205 minus 200.5 divided by 522.5. And did y'all get something for that? So you definitely need your calculator, right? 112.57 about, if I round it off, 56557. Okay, so yeah. Yeah, that's got to be right? Slightly less than 120 degrees. See, you knew theta was in the second quadrant, unless that really got pushed off, of course, right? Theta was going to be in the second quadrant. And so when you get this angle in the second quadrant, you're confident that that's going to be correct, right? If you instead did the sine inverse of this number, you'll get an angle in the fourth quadrant, which you know is not correct, right? And so you'll have to adjust that to an angle in the second quadrant. So using cosine inverse here is much more practical than using sine inverse. Okay, so I think that you're going to follow those the same steps, right, in problem 14 on the home to find the magnitude and direction of some resultant vector. Okay. All right, so any more? That's our last example. Finally, from two-dimensional vectors. Yes. Oh, okay. I thought that was our last question. All right, so question 12. Did we not do one like this, Fatin, also? Oh yeah, we did one like this. So so you cannot look at the example. Yeah, it's this example. Let me see if I can find it. It's this example from the notes that we went through last time. Okay. Is it somehow markedly different from that example? Yeah, that's right. Oh, I see. Okay. Yeah, so that does make it ugly, right? We can certainly start this though, to just remind ourselves of the steps. So the function is tangent. So there they've got some nice graphs of the tangent curve, right? And so the tangent curve apparently passes through the point pi over 4 and 1. So you can test that, right, by computing the tangent of pi over 4 and see if it comes out to be 1, which it does, because sine and cosine are the same at pi over 4, right? They're both the square root of 2 over 2. So if you divide sine by cosine to get tangent, we'll of course get 1 there, right? So indeed, the tangent of pi over 4 is 1. So let's write this down then in the notes, and let's just sort of skim over what one needs to do to solve this one. So we have our function is the tangent, right? And we have this point pi over 4 and 1, which is on that graph. And then we want to find a vector that is it a unit vector we want that is parallel and perpendicular to the curve at this particular point? Okay, right. Um, so again, the parallel to a curve, as we mentioned last time, that terminology is a little bit incorrect because parallel refers to lines, right? Lines can be parallel, but curves are not parallel to one another, right? Or something cannot be parallel to a curve. So when you say, I want to write something down that's parallel to a curve, what you really mean is parallel to the tangent line to the curve at that particular. Okay, so you need to be able to treat the curve like a line, which it's not. The tangent curve is certainly not a line, but to treat it like a line, then instead you'll substitute the tangent line for the curve. But tangent lines, of course, change at every point of a curve, right? Okay, so you have to know a specific point that you want something parallel to the curve, right? Well, here they're telling you at the point pi over 4 and 1, okay? And so how do we find tangent lines, of course? Derivatives, right? Yeah, you have to do derivatives, right? Okay. So in fact, as we emphasized last time, right? The slope of the tangent line at a particular point is the same as the derivative at that point. So if we can find the derivative of tangent x at the point pi over 4, 1, right? Then we will know the slope of the tangent. Okay. All right. So well, what is all right? So now we have to remember a little bit of calculus 1 though, because what is the derivative of the tangent? Secant squared, right? So that's secant squared. And so if we compute f prime of pi over 4, right, then indeed we have to know the secant squared of pi over 4. Yeah, right? But secant is, how can you convert secant to, how can you convert secant back to sine and cosine? Yeah, the secant is the inverse of the cosine, right? Or the reciprocal of the cosine. Maybe the right way to say that. So this is really 1 over cosine squared of pi over 4. But what's the cosine of pi over 4, as we've said now like a million times here? Because pi over 4 is 45 degrees. So the cosine of that's what? Yeah, square root of 2 over 2. And we have that squared, and then we have the reciprocal of this, right? So if you square this, you get, what, 2 over 4? But then you have to take the reciprocal of that, and that gives you what, 4? Yeah, 4 over 2, all right? Or you can write that if you want to, I guess, as better known as what? 2. Yeah, okay, right. So so there's the slope of the tangent. Now you can use that really quickly then to find the vector. Okay, use that really quickly there to find the vector, a vector, right? Not a unit vector, but a vector that is parallel to the curve at this point. Because remember, this is a slope, right? And as we saw last time, right? Remember, you can interpret a slope geometrically as what? Rise over run, correct? So that means that tangent vector that you're looking for, you can create that by taking a rise, a horizontal component of 4, and a run, a vertical component of 2. So that vector is parallel to that curve. Okay. This is written in component form, which is fine, right? And then how do you So they wanted a unit vector, right? So how do you turn that into a unit vector? Yeah, just divide by the magnitude, right? So your unit tangent vector be this vector, right? Divided by the magnitude. So I think the magnitude there is, looks like square root of 20 to me. So 2 over square root of 20 and 4 over square root of 20. So there's which by the way could reduce a little bit because you can simplify square root of 20. By the way, you could have used 2 as well, right? It would have been easier. Could have used 2 as well to create this vector because 2 is, if you write that as a fraction, that's what? 2 over 1, right? So another tangent vector would have been a run of 1, a horizontal component of 1, and a vertical component of 2. Okay. So over, to the right 1 up 2, right? That vector also would work. That's just a shorter version of this vector, right? And here's an even shorter version of both of these vectors, right? Because this is a unit vector. Okay. Now you're going to see how to do the perpendicular one because you just have to find now a line perpendicular to this a line, right? A line perpendicular to this line is going to have, I'm sorry, a line perpendicular to the tangent line is going to have negative reciprocal slope of this 15. So just write the negative reciprocal of this, which would be what? Minus 2 over 4? Yeah. Okay. So minus 2 over 4. And then create the vector there. Okay, I was going to mention that I'm in the Math Center from 2 to 5, but um, I get appointments with students, and so if you're going to come see me at that time, you may want to make an appointment with me. I think if you go to this announcement, there's a link here to the Math Center. You can, there are instructions here for making an appointment with people in the Math Center, and you can find me and make an appointment with me for between 2 and 5 if you're going to come see me on Mondays and Wednesdays. Now, that's a little bit inconvenient though, because if my appointments get booked up, then you won't be able to spend time with me unless it's just a simple short question, right? Or if you're going to give me something. So I'm also in my office before class. So my office is South 611. I think it's here, right? Did I say what my office was? Oh no. Well, my office is South 611. That's probably on the syllabus. And so before class, you can also find me. So, but it would be better to email me and let me know that you're coming, right? And then, so then you won't have to book an appointment, right? Just let me know that you're coming before class, and then we can meet then also. Okay, if you have time before class. Okay. All right. Let's change notes here then. Oops. All right. Let me remember to pass out the roll. So I'm going to pass out the roll now. So what you're going to do is sign in the first available slot. So what you're going to do is sign in the first available slot, and then remember your number. Right. So if it's an easy number to remember, it won't be difficult to remember it. But if it's an unusual number, then write that down somewhere or make a note of it in your phone or something, right? Because you want to sign in the same place every time. So make sure you sign in the same spot every time. And don't sign in somebody else's spot. So make sure you sign in the right spot, because we get all sorts of conflicts that arise when this happens. So so just remember your number and sign in that slot. So sign in the first available spot. Don't skip any slots. So C for Amber, that's easy. She's gonna be so. Okay. But if you're some 7, some other 13 or something, then write that down somewhere so you'll remember where to sign, right? Okay, so that's going to go all the way around and don't lose it. Okay. So now we're going to finally, since this is calculus 3, right, we're going to switch to 3 dimensions. And so we're going to talk about vectors in 3 dimensions instead of 2 dimensions. But fortunately, everything sort of translates very well to 3 dimensions. So sort of all the things we learned about vectors in 2 dimensions, we're just going to translate it into 3 dimensions. Now, what's hard, however, is getting used to working with 3-dimensional space. That's the tricky part. Because you're used to in math classes doing everything in 2 dimensions, and now when we're expecting you to work with 3 dimensions, even though we live in a 3-dimensional world, right? So we're very accustomed to the 3 dimensions, but somehow when you're trying to do math in 3 dimensions for the first time, it gets kind of boggling. So you have to get comfortable with that. But the vector concepts work very similarly. So you know, you can extend the familiar rectangular or Cartesian coordinates, right, to 3 dimensions just by adding a third axis that is perpendicular to both the x and the y axis. All right, and this is so you get kind of a 3-dimensional picture, and this usually that third axis is labeled z. Okay, so we have the x-axis and the y-axis and the z-axis, right? And then you locate a point in 3-dimensional space, just like you do in 2-dimensional space. This is still the Cartesian coordinate system, so the point location idea is the same. You know, you're going to give the location of the point. If you're thinking of a point in 3 dimensions, you give a location of the point with respect to the x-axis, with respect to the y-axis, and then also with respect to the z-axis. And when you have those three when you know those 3 positions, then you've got the point nailed down, right? You've got the point perfectly located. The problem is trying to do this on paper is that paper is 2-dimensional, right? So we're trying to represent a 3-dimensional idea, right, on a 2-dimensional space, and that's the part that gets a little bit sometimes gets a little bit messy. All right, so here's kind of a picture of the 3-dimensional coordinate system, 3-dimensional rectangular coordinate system, but that's been drawn on a flat surface, right? So so there's a little bit of perspective involved. But anyway, here's you know, it's the setup here is exactly what I said, right? You have the x and the y axis just as usual, right? And then perpendicular to both of those, here you have a third axis, which we usually label the z-axis, right? And it's just a number line, just like the x-axis and the y-axis is a number line, right? So you've just inserted a third number line here into the picture. And if you want to locate a point there in that 3-dimensional space, right? Say we have this point, and we want to give it a location in the 3-dimensional space, right? Then you do that just like you do in plain old 2-dimensional coordinates, right? You give the location with respect to the x-axis first, and then you give its location with respect to the y-axis, right? And then you give its location with respect to the z-axis, which is kind of going to be its elevation, right, above or below the xy plane, right? So that z dimension is kind of the height there, so to speak, right, of the point, right? So we've just got the regular old xy plane, right? And but we've just added this third dimension in, right, with this extra axis here, the z-axis. Now, here's what's going to be sometimes confusing, though, when we're working with 3D coordinates. Since we've represented this on 2 dimensions, we're sort of looking at this 3-dimensional set of axes, right, from a particular perspective, right? So you see what I'm asking here, or what I'm talking about here? we're sort of looking down, right? Okay, the observer is sort of looking down here on the XY plane, or looking down on this 3D picture, right, from a particular location and in space, right? Okay, so you are actually occupying a point there yourself as the observer in three-dimensional space. Okay, now I don't know what point you're located at, but kind of what's implied there. Where is that point located at? Okay, so see, that's the question that I'm asking here. Where are we observing this three-dimensional set of axes from? We're, yeah, we're kind of floating above the XY plane. That's kind of clear, right? Okay, we're above the XY plane here because we're looking down on the XY plane, right? Okay, so we're above the XY plane. Well, the XY plane has 4 coordinates, right? So we're hovering above which quadrant are we? See, right? Okay, we're above the XY plane, but where above the XY plane are we? Yeah, it looks like here we're above the first quadrant, right? I would say we're above the first quadrant, right? We know this is the first quadrant, right? Because here's the positive side of the x-axis, right? There's the positive side of the y-axis. So this has to be the first quadrant, right? And we appear to be somewhere there, looking at this, somewhere above that first quadrant, right? I don't know where, but that's where we're observing from, okay? So I think here it looks like we're above the first quadrant, right? Above quadrant 1, right? In this the way this is drawn. But you can draw these 3 axes from different perspectives. So, and that's sometimes confusing. So you can draw as though you were looking below the XY plane, right? Okay. So you are sort of down on the negative side of the z-axis, right? So you can be looking up at the xy plane, or you can be sort of hovering above. Even if you're above the xy plane, you can be hovering above different quadrants. Okay, right? So you don't have to always be looking sort of down from the first quadrant, right? You can also be here in the, which quadrant is this one? Be careful. That's the 4th quadrant, isn't it? Right? Okay. See here, why? No, am I right there? No, maybe I'm wrong. Yeah, so this is negative x and positive y. What's that? Oh, that is so this is the 2nd quadrant, right? And then over here is the 3rd quadrant, and this is the 4th quadrant. Is that right? Yeah, positive x and negative y, right? Okay. So you can draw this picture from different perspectives, where you might be sort of looking down from different locations, or looking up, as it were, there from different locations, right? Okay. And that you have to kind of adjust yourself to when you look at a three-dimensional graph. Okay. But the location of the points, right, is the location of the points there is easy to understand. Okay. All right, let's just to show you what I mean here. Okay. All right, there. I think those are the same 4 points. Okay. Those are the same 4 points that were plotted in that first picture, right? But now we're sort of looking at things slightly different. This picture was drawn using Wolfram Alpha to plot those 4 points. Where are we? Yeah, what's strange about this one is they haven't really drawn the XY plane right? Okay, this sort of bottom of this box, right? That's not the XY plane, right? Because that is at -2 on the, that's at -2 on the Z axis, right? The XY plane is somewhere here. Right? That's at 0 axis. Okay? But now let's see. So there's the X axis, though, right? So it's running left, right, from negative to positive, right? What's the Y axis doing? So in this direction. Also negative to positive, right? Okay. So I think we're above, now we're like above the up, right? Because see, there is X running left to right from negative to positive, right? Like, probably like far enough, right? And then there's Y running back to front, also positive. So we're kind of in the negative side there, Y axis, right? But on the positive side of the X axis, I think kind of in kind of think of ourselves as being somewhere like this three-dimensional boxes. These points make any sense? What does it look like? It's very hard to pick out points now. What does it look like the coordinates of that point are, for instance? Zero. Okay. Yeah, the origin is right here, isn't it? Yeah, it's pretty much in the center of the box, right? But for that point, that particular point, right? I think that's laying on the base of this box, right? So the base, that's the idea I think I get here, right? This is laying on the base of this box, which is where on the Z-axis? Yeah, there's the Z-axis, right? So the base, it looks like the base of that box is around -2, right? So is that -2 on the Z-axis? Where does it look like it is on the X-axis? This is 2, this is 3 on the X-axis. So that looks like 3, I think. And then what about for the Y coordinate there? Wow, it's very hard to tell. Is it positive Y? If we go across here, is that -2? See, here's 0, Y, like this, right? So this point is a little bit, or is it at 0? Or a little bit. Y 0 down. Mm-hmm. Will be about. Mm-hmm. And then draw like this? Yeah. Oh, so it's actually positive there? Oh, I see. Okay. So see what's so weird about this, right? So maybe 2 or 3, is that what? Yeah. Well, we can cheat because we know that these were the same points as up here. So is this it? 3, 3, and -2? Yeah. Oh, it came pretty close, right? So there is really 3, 3, and 3, 3, and -2. So the moral of the story here, it's no picnic, okay, to plot things in 3 dimensions. All right. So it's going to be a challenge when you're doing it by hand. Fortunately, we do have some tools that will help us. Okay. So we're not going to be doing a super amount of 3-dimensional plotting, but we will be doing some by hand, and doing it by hand will help us understand a little bit by hand will help us understand what we're seeing on the screen. Okay, we get software to do it for us. Okay, so we'll do some we'll try to do some 3-dimensional plotting by hand. In fact, we're going to do this right now, I think. Okay. So do y'all have some graph paper? Okay. Got some graph paper there? So what I want you to try to do here, okay, for me is wow. Let's draw a three-dimensional Cartesian set of axes, right? Three-dimensional Cartesian set of axes. But I want you to draw it as though you were above, so you can be above. Below is going to be difficult to think about, but above quadrant 3. Okay, so above quadrant 3. Now, let me give you some. Let me tell you how to make this a little bit easier. We're not perfect artists, right? So go ahead and draw a axis straight across, right, horizontally, and then draw an axis like this, all right, so that appears to be a plane, right? Does that look like a plane to you? We're looking down on a plane, right? Okay, and you can let this be the XY plane. So if you want to, this can be X and this can be Y, or you can reverse those. That's fine also. So then, of course, Z would be coming up like this, right? The only question is, how are you going to label the numbers along the x-axis and along the y-axis, right? Because you want it as so you're looking down from quadrant 3. So I want this to be quadrant 3. Is that possible that we can get that? Okay, we're looking down from quadrant 3. So you got to put tick marks here, right? You got to put tick marks in here. So the only question is, how will I label those tick marks? Are they going up? Are they going down? And right? Okay. Uh, for the tick marks on the y-axis or this axis that's running from front to back, you may want to skew those a little bit, right? So you get kind of a more three-dimensional perspective. See what I'm doing there? Kind of make it look more three-dimensional. I guess I probably could have tilted these two a little bit to make them look. Probably should have tilted them like this, right? To make it look like, to give us a little bit of illusion of 3 dimensions. Okay. All right. So just on your sheet of paper, try doing that. You may want to give yourself quite a few tick marks on the left and the right. So maybe up to at least 5, maybe up to 8. I don't know if you have to go to 10. Okay, because we're going to use this. All right. So make it pretty big because we're going to use this in a minute to find some things. Okay. Right. So gonna come around here. There you go. Yeah, so you find so this is gonna see it. So, 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 so so yeah, well, I guess see.
Z. R. So, for so, so, yeah. So, that used to label. Yeah. Kind of like that. Kind of like we have. That what you were thinking of? Like, are you seeing it's, it's, so, it's, still, yeah, it's hard. Very good. All right, guys. Do y'all have a suggestion? Does someone have uh, something something they want to suggest there that they think is okay? Can you start from this picture? Does it make sense to start from this picture? Can you do it from this picture where the x is like this and the y is like this? To get above the third quadrant, yeah. Yeah, I'm currently above the fourth quadrant, right? Okay, but I don't have the x and the y labeled, right? So that could have an influence on it, right? So if I put if I put x positive here, y negative here, that's indeed going to be the fourth quadrant, right? Okay. But can I think of this differently? Would it make sense to do this? is that perspective possible? How would you be how would you be positioned so that you could see it like that though? Possible to be above the XY plane and see that? Yeah, I don't think if I'm above the XY plane, I'm gonna see the number. Want this, see, if you want this, like this to be above, like above, like, think about staring down above the third quadrant, right? So if this is quadrant B, above that, now what's this gonna, what's that gonna, that would be not even the x-axis, right? That should be the y-axis, right? Okay, yeah, because that's gonna y-axis, and this, yeah, this could be x-axis, right? So this labeling is correct on the tick marks, except what do I have? I have to switch to x. Okay. This helping at all, right? So you think about drawing just drawing a plane, right? And now, see, this is the third quadrant. See, uh, the y-axis, right? As left to right, x-axis direction. The negative on the y-axis. So you can negative on the x-axis, right? So you can make this work for a third quadrant perspective, but this has to be y and this has to be instead x. Okay. Someone else do it differently? Wait, Ricardo, you did it differently. What did you draw? Yeah, come show us that one. You draw it quickly. Just scribble it on here what you drew. Or just describe to me what you drew. Or actually. No, just bring yours. Just look at it. See if we can switch to the. See if we can make the document camera work. Yeah, there. Try laying it there, and we'll try laying it there. So can y'all see that? Oops, perfect. Ooh, so describe that to us, Ricardo. Why is that correct?
I just
Oh, so he drew it he did draw it slightly differently, right? But
I just rotated the y-axis
Mhm.
to make it look like the illusion that we're above the third.
All right,
quadrant.
so there's the XY plane, right? So we're in above this portion, right, of the XY plane, and indeed, Y is negative there, right? And X is also negative, right?
Yes.
Yeah, okay, so, oh, perfect there, right? So I think indeed, we're above there we are above, right? Okay. Ooh, nice, okay. So he solved the problem just by changing there a little bit the way he drew the X and the Y axes. Okay, good. Yeah, right. Okay, well, see, we have to draw these 3D graphs from time to time, right? So, These are the sorts of things you have to think about, right, when you're looking at them. All right, so now some of the things we know about two-dimensional coordinates, they move over to three-dimensional coordinates really well. So you're already familiar with these things. Like the distance formula in 3 dimensions is same as the distance formula in 2 dimensions. You just add in an extra term under the radical, right? Okay. So if you want to find the distance between, if you want to find the distance between, two points in 3 dimensions, you just take the difference in the coordinates, right? Square them, and then take the square root, right? So distance formula works out beautifully, okay, in 3 dimensions. And the midpoint formula also works the same in 3 dimensions as it does in 2 dimensions. So if you've got 2 points in 3 dimensions and you want to find the point that's halfway between them, you do the same thing that you do in 2 dimensions, which is you average the coordinates. So if you've got these 2 points and you want to find the point that's halfway between the 2 points, just take the average of the x, y, and z coordinates, and that will give you the midpoint. So that familiar midpoint formula from 2 dimensions is really the same in 3 dimensions, and that familiar distance formula in 3 dimensions is really the same as it is in 2 dimensions. Now, here's where things start going awry, though. Okay, because in 2 dimensions, right? If you have an equation in 2 variables, that defines a curve, correct? So, so in 2 dimensions, if you have an equation involving x and y, if you plot the solutions to that equation, you will get typically a curve. So here is there's the famous formula for a circle in 2 dimensions. X and y are the variables here. X0 and Y0 are the center of the circle, so these are constants. And of course, R here is the radius of the circle. So if you plot the solutions to this equation, x and y are the variables. So if you plot the solutions to this equation in 2 dimensions, you get a circle, right? If you take the squares off and simplify that equation, you get an equation that looks something like this: x plus y equals r. Of course, if you graph this equation in 2 dimensions, you also get a curve. What does the graph of this curve look like? No, it's even simpler than that. That's a straight line. Okay, so that's the graph of that's just the equation for a straight line, right? You can see that probably more easily if I write it like this. That look like a linear equation to you now? Yeah, what's the slope there? -1, right? And what's the y-intercept? R, whatever that value R is, right? Okay, so so this is the equation for a straight line. There's the equation for a circle, and of course you can write all sorts of equations down with 2 variables, x and y, right? And they give you different sorts of curves in 2 dimensions. Okay, well, in 3 dimensions, if you write down an equation with 3 variables in it and plot its solutions, you're also going to get some sort of picture, right? You're going to get some sort of object. The thing is, the objects in 3 dimensions now are going to be much more complicated, all right? So let's take this equation, x minus x0 squared, y minus y0 squared, z minus z0 squared equal r squared. That looks like the equation for a circle, right? Except all we've done is added in this one extra term. If you graph the solutions to this equation in 3 dimensions, you get a sphere, okay? So that's the equation for a sphere in 3 dimensions. So not a curve, but an actual object, right? An actual 3-dimensional surface, right? The center of that sphere is, by the way, x0, y0, and z0. Now, You may wonder, well, what happens if I take off the squares here? So what if I have an equation in 3 dimensions that looks just like this? And I plot the solutions to that equation in 3 dimensions. Wonder what sort of thing I would get. You may think, oh, I'm just going to get a straight line. Okay, so I'm going to get a straight line in 3 dimensions as opposed to 2 dimensions. And the answer is no, you get a much more complicated thing in 3 dimensions than just a straight line. Okay, so typically solutions, graphs of equations in 3 dimensions are going to be surfaces. They're not going to be curves. Okay, so they're not going to be simple curves. They're going to be complicated objects, complicated surfaces like spheres or other sorts of 3-dimensional objects. This turns out to be a plane. Okay, so when you graph this equation in 3 dimensions, you don't get a straight line, you get a whole plane. All right, in the 3-dimensional space. Okay, a flat plane. All right, of some sort. Here, I'll give y'all a simple example here. I've already drawn a picture of this. So find the equation for me of the sphere in 3 dimensions that has those 2 points as endpoints of a diameter. So if you drew a line all the way through the middle of the sphere, you would have on one side this point 5 minus 2, 3, and then on the other side you would have this point 0, 4 minus 3. Okay, so those are endpoints of a diameter. What's the equation for that sphere? Here, by the way, is a picture of that sphere. So there's a picture of that sphere. Notice we appear to be looking at that sphere from underneath, right? Okay, so we are looking at that sphere from bottom up. So we're kind of below what plane are we below here? What quadrant are we below? Kind of true. Let's see. There's the positive part of the x-axis, and here is the this is the negative side of the y-axis. Right? So I'm below what? Is that quadrant 4 below quadrant 4? Positive side. Oh, I'm going from yeah, from 0 to positive on the x-axis and then from 0 to positive. Is that below? So, we're going negative y in this direction, positive x in that direction. That's covered. Yeah. Okay. So somewhere down below quadrant 4, that sphere. That's the sphere that I want you to. The sphere that I want you to write. And we can. Well, it's very so. You see, it's very hard to plot points. We're told that what points were on that sphere? Are were endpoints of a diameter of that sphere? 0, 4, and minus 3. Can I even find that here on this sphere? There's x equals 0. So that's like on this part of the sphere. And then what? 4 on the y-axis? Oh, very hard to find, right? On the other side, it's on the other side. Yeah. Okay. And then minus 3 on the z-axis, somewhere right. Yeah, see, very hard to find, very hard to locate those points. We'd have to think about that for a while. What's nice is latitude on in speaker, right? So sometimes I can help you look speaker, right? Since x equals 0 probably corresponds to this latitude sphere, right? So x that sphere. I equals C. Sorry, Z equals what? Right? Well, locating the points is harder than even writing down the equation. So what is the equation for this sphere? Well, remember I told you here is in general, there's the equation for a sphere in 3 dimensions. What do you have to know? You have to know the radius, right? Okay. And you have to know what? The center of the sphere, right? These 2 points, though, are on the surface of the sphere. They're not the center of the sphere. But how do we find the center of the sphere then? Just find the midpoint, right? Okay. So just compute the midpoint. That's going to be the center. So that's easy to do, right? In 3 dimensions, just like it is in 2 dimensions, just take the average of your coordinates. So average the x coordinates. That looks like what? 5 halves. Average the y coordinates. That looks like, I think, 1. And average the z coordinates. I think that turns out to be 0. Just add, divide by 2, right? 5 plus 0 divided by 2 minus 2 plus 4 is 2 divided by 2 is 1. 3 plus a minus 3 is 0, of course, divided by 2 is 0. So there's the center of the sphere. And to find the radius, oh, that's uglier. How do we find the radius? Well, take the distance, right, between these 2 points. That's the distance all the way across the circle. So how would you find the radius? Just divide by 2, right? Okay. So find the distance between these points and divide by 2. Let's see. So that's going to be 5 minus 0 squared, right? Plus minus 2 minus 4 squared plus 3 minus a minus 3 squared, and then divide all of this by 2. Let's see what we get here. Can I do all of that? That looks like 25. This looks like 36. Is that right? And this looks like 36 again. Divide all of that by 2. Well, we don't have to simplify that. That's what, 97? Square root of 97 divided by 2. So there's your radius. So how do you fill in the values there? We have x minus, what's the x coordinate of the center? 5 halves squared plus y minus the y coordinate of the center, which was what? 1, right? Squared plus, and then z minus 0, the z coordinate of the square, of the center squared, right? And then take that radius and square it. Did I calculate that distance correctly? I hope so. So there's the actual algebraic formula for that nice sphere that we see here. It looks like a football, but that's just the way it's drawn in Wolfram Alpha. That's really a sphere. Yeah.
I see.
Because these were endpoints of a diameter. So Elijah, these are actually on the surface of the sphere. And so if we find, and they're at the end of a diameter, so the line that goes between these 2 points, it goes right through the center. So I don't know where the 2 points were. That was the controversy, right? Where are those 2 points? We only need the radius, right? Yeah. Okay. So we found that total distance and then divided by 2. Yeah. Sure. Yeah. Yeah. So once we had the midpoint, then we could just find the distance from the midpoint to one of the 2 points, right? But that's a little bit messy because that midpoint had a 5 halves in it. So I was trying to avoid that. Okay. Using that, right? Okay. Okay, well, we're almost out of time, but we've just got to where the important thing here, which is not these surfaces. We'll come back to surfaces later, all right? But what we're really aiming for here are vectors. And vectors in 3 dimensions now are going to look very similar to vectors in 2 dimensions, except you have a third component, right? You have a component that is parallel to the z-axis. So vectors in 3 dimensions can be written as linear combinations of these 3 unit vectors. So 1 unit on the x-axis, 1 unit on the y-axis, or 1 unit on the z-axis instead, right? That unit vector that is parallel to the z-axis, we call that k. All right, so we have I, j, and k, right? A nice alphabetical order there. And so at least initially, vectors in 3 dimensions are going to be very similar to vectors in 2 dimensions, except they're just hard to graph. Okay, right? Okay, because you have to graph them in. Unfortunately, you have to graph them 3 dimensions, right? And that's going to be a challenge for us. Okay, is thinking about these vectors in 3 dimensions. But we'll get over that. All right. So, what perspective are we? What's this perspective, by the way? So we're above what quadrant here? This is the y-axis and this is the x-axis. So is that still the first quadrant? Yeah, that's still the first quadrant, right? So we're right above the first quadrant, right, in this picture. Okay, well, so we're going to take this up next time. Is working with 3-dimensional vectors, but this will all be very familiar to you. And we're going to make, and we'll have one force application, but it's exactly like 2-dimensional force application. All right. Okay. But in 3 dimensions, the vectors are really going to be useful to us and help us understanding the graphs of surfaces, because the graphs of surfaces are complex, but vectors really turn out to be a very useful tool in helping us understand what surfaces look like. Okay. All right. So let's stop there. The computer says rain. Is it raining outside? Bummer. And I'll see you again on Wednesday, right? So I won't see you on Monday. Okay, so be working on that second homework too. I don't know if we're not through all the notes, so we may have to extend that due date, but see how much of it you can do at least. May be able to do some of it. Okay. Yes. Wait, say that again. Oh yeah, those are videos from the textbook. Does the link still work though? Did you try clicking on it? Okay, yeah, those are just things that I lifted from the from textbook videos. So sometimes they're good and sometimes they're, I don't know where they get them from. Okay. Yes.